that same table of primitive roots that I gave you on the second exam, I'm going to put that on the final as well. So you could just look at that table and it will tell you a primitive root. Let's just remember what a primitive root is again. So a primitive root is an element that has the maximum possible order, which is phi of whatever the modulus is. What is phi of 13?
12.
It's just 12, right? Phi of any prime is just that prime minus 1. So we're looking for an element of order 12. Okay? So every element in mod 13 has order that divides 12. So the possible orders would be 1, 2, 3, 4, 6, or 12. You want to find an element that actually has order 12. What would be your first guess? 2. Let's try it. Okay? Reduce mod 13 with me. Is 2 to the first congruent to 1? No. 2 squared congruent to 1? 2 cubed? No. 2 to the fourth? 2 to the fourth is 16. In the world of mod 13, that's not 1, right? 2 to the sixth, which is 64. In the world of mod 13, what is that? 64 is actually negative 1, right? In the world of mod 13, because 65 is a multiple of 13. So none of these powers of 2 are congruent to 1. So the order, the conclusion is, so none of those work. So the order in mod 13 of 2 is indeed 12. So 2 is a perfectly good primitive root to use. Okay? Is everybody with me? How do you get the other primitive? How many primitive roots does 13 have? Phi of 13, right? This is just a side issue. We've got our primitive root now, but I just want to make sure everybody remembers this. So phi of 13, when phi of 13 is 12. Phi of 12, those are the numbers that are relatively prime to 12. You can either just list them out, or you can figure out how to factor this. It's just going to be phi of 4 times phi of 3, which is 2 times 2, which is 4. Okay. So there's 4 of them, and basically you're looking for the 4 numbers that are relatively prime to 12, and those are the powers that you're going to take. So for the primitive roots of 13, you start off with a primitive root that you've already found, and then you just simply raise that primitive root to the powers. Look at those powers. Those powers are exactly the numbers that are relatively prime to 12. Of course, they could be reduced again modulo 13. But this is what you would have so far. Okay? So let's just take 2 as our primitive root. Okay, so when I take the index here, remember that we have our nice properties of index, yeah? So the 6 comes down, and we multiply by the index with respect to 2 of x, congruent to the index with respect to 2 of 12. And what is this congruence, what modulus is that congruence going to occur in? In phi of 13, exactly, which is 12. That's exactly right. Okay. I'm going to go ahead, and this is just by way of review as well. Let's just make our table of indices again. Do you remember this? So you take all of your numbers on top, and you're just going to take their index with respect to 2 and draw that table here on the bottom. So let me put the numbers here. The numbers that you put on the top are just the numbers that are relatively prime to 13. Well, that happens to be every number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay? So you're just going to put all of those numbers there. And you're asking, for each choice of A, you're asking what power of 2 would be congruent to that. So for example, 2 to the 0 is congruent to 1. Right? 2 to the first power would give you 2. 2 to the second power would give you 4. Right? 2 to the third power. So the power is going on the bottom row, and 2 to that power is on the row above it. 2 to the fourth power is 16. But I'm reducing that modulo 13. Guys, when you're reducing the powers of 2, you're still doing that modulo 13, not modulo 12. People sometimes get confused about which mod they're working in. The index equation is the one that's mod phi of n. But the original equation where you're just reducing things modulo 13, that's the original mod that you're working with. So 2 to the fourth power is 16, but in the world of mod 13, that would be 3. Okay? If I multiply by 2 again, I'm going to get 6. So the fifth power of 2 is going to be 6. If I multiply by 2 again, I'm going to get 12. So the index of 12 is 6. 12, that's the same as negative 1. So if I multiply by 2 again, I'll get negative 2, which is the same as 11. So that's going to be where we put 7. Okay, multiply by 2 again, we get negative 4, or in other words, positive 9, so that's 8. Okay, if we take 9 and multiply by 2 again, we get 18, but in mod 13, that's 5, so the 9 goes there, and then we double that to get the 10, going with 10, and we double that, which gives us 20, but in mod 13, that's 7, so we put 11 there. This 0 over here, you could change it to a 12 if you prefer. Again, we're looking at these values on the second row in mod 12. Okay. So is everybody comfortable with the table there? Now, we have to figure out the index of 12. Okay, that's what we need for this problem. So the index of 12 was 6, right? The very last entry over here, so this is a 6 right here. Oh, that's kind of handy. I got factors of 6 that I can cancel out. So the index with respect to 2 of x would be congruent to 1 mod 2. Does everybody see that? I got a 6 here, and a 6 here, and a 12 there. I can cancel the 6 and the 6 and the 12, and it reduces down to this expression right here. In other words, we're just saying that the index of x should be odd, right? So the index should be odd. So where are the odd values? The odd values are here, 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 and here, right? The ones I underlined. So what are the x values? To get the x values, I go back up to the top row of the table. Okay? So are you with me? So I'm taking these numbers on the bottom, I'm looking right above them. So x is congruent to either 2 or 5 or 5 or 6 or 7 or 8 or 11. And that is modulo what, by the way? On the top row, that one is mod 13. Guys, remember, the top row is mod 13. The bottom row is where we essentially are doing mod 12. Okay, so let's be a little careful with that. On the mod 13 table, we don't have an entry for 0. The first row starts from 1 through 12. Right? On the bottom row, we have exactly the same number of numbers, but we're looking at it modulo 12, and we're including 0 as one of our choices. So that makes up the difference. Or that's why there's the same number of entries on both rows of that table. So this is mod 13. Okay? So all of those, this is very bad news, because we just found 6 different x's that solve the first congruence up here. Okay? So I hope you guys like the Chinese remainder theorem, because we basically have to take each of those 6 choices and pair them up with what we already have on the second equation. So maybe we won't do all of them, but I'm more than happy to do 1 or 2 of them just to make sure we all remember how to do this. I know you've been doing it recently. Some of you even put examples of the CRT into your term papers, so you even typed up a few examples of this, but so there's several cases to do here. So like the first case would be x is congruent to 2 mod 13, and x is congruent to 11 mod 25. Okay? Do you guys all remember how to do the CRT process? The solution, remember, is x is congruent to a1, n1, y1 plus a2, n2, y2. And this will be modulo the product of those mods, 25 times 13, which is 325, I believe. The A1 is 2, and the A2 is 11. Those numbers are easy. Remember that capital N1 is the product of all of the other n's besides the first one. So capital N1 would be 25. Capital N2 would be 13. So I'll put 25 here, put 13 there. And then we got to figure out the Y1. So remember that N1, Y1 is congruent to 1 modulo little n1. So 25 y1 is congruent to 1 modulo 13. So what is y1? Can anybody solve that in their head? What is 25 the same as in mod 13?
1? Is it negative 1?
Mm-hmm. Yes, that is right, because 25 is the same as negative 1, right? So then y1 would also be negative 1. That's right, so y1 is congruent to negative 1. Okay, so I'll put a negative 1 there. All right, and then we've got to do a similar thing for the n2. So capital N2 times y2 congruent to 1 modulo little n2. So capital N2 is 13. Y2 congruent to 1 modulo 25. Can anybody eyeball that one and give me an answer? It's 2, exactly. So just figure out what the y2 is equal to 2. Again, if you're nervous that it's not always going to be that easy to just look at it and see the answer, remember that you can always use the Euclidean algorithm to find the y2, right? Okay, so we'll put a 2 in there. So we start working this out. 13 times 11 is 143. And then when you double that, you're going to get 286. But then you have to subtract 50 from that. So 286 minus 50 is 236. Is that anything close to what I got in my notes? I did, yes. I also rewrote that. If you prefer to write it as a number that's closer to 0, you could use negative 89. But you don't have to do that, okay? So there is one solution. 15 minutes later, we have one solution. Okay, so I think the other 5 cases are very similar. Can I just leave that to you guys for practice? On a test, you have to keep in mind with a final especially, I'm not interested in testing you on the same thing over and over and over again. So I probably would say something like, find any 2 non-congruent solutions to the system. Okay, so this would be one of them. And then to get another one, you'd have to do one more of these cases, and you could choose which of these other cases you would want to do. So I might make you do it twice, but I'm not likely to make you do the same thing 6 times. When I'm doing review session questions, I don't stress about it quite as much that my problems are like perfectly formatted for an exam, but basically that would not be a good question to have six of the same thing on there. Okay, we've done a lot this semester. I may as well ask you about a lot of things. Does anybody have any questions on this one? Yeah, Gina?
For the possible orders, we chose a few, I forgot why. So you choose any number
All of
and then
these?
you put, yeah.
So it's just all of the divide. So the order modulo n of any number always divides phi of n. So phi of 13 is 12. The divisors of 12 are just all of these numbers here. So every number is going to have an order that's one of those 6 things. And we just needed to find one that had order 12, which happened to be the first one we tried worked. Yeah. Make sense? Okay, any other questions so far? Making sense? Okay, let's do another example. So I only did one case here. I did not solve this whole problem. Found one solution, but there's going to be several others. Okay, let's do number 3 right here. Let's prove that there are no perfect numbers of the form 3 to the I times 5 to the j with I and j greater than or equal to 1. You can obviously, if either I or j is 0, then you know, that would. Well, let's prove that there are no perfect numbers of this one specifically. Okay, let's not worry about powers of. Actually, it's pretty easy to show that a power of a single number cannot be perfect. So, but this is actually a slightly harder example. So remember that perfect just means sigma of n equals 2n, right? So how would you suggest we proceed here? By contradiction? Okay, so we could say, for the solution, let's assume by way of contradiction that 3 to the I times 5 to the j is perfect. Okay. So what does that mean again? That just means that sigma of 3 to the I, 5 to the j is equal to 2 times 3 to the I, 5 to the j. Okay, that's what it would mean if it was perfect. Okay, what can we do with that? Figure out the sigma over here. We have a formula for sigma of any number, right? Basically, what is sigma of any number? You factorize the number into powers of primes, which actually is what we already have. And remember that sigma is multiplicative. So sigma is multiplicative, respects multiplication. So in other words, sigma of 3 to the I times sigma of 5 to the j equals 2 times 3 to the I times 5 to the j. And we can write down the formulas for sigma of a power of a prime, right? Remember sigma of 3 to the I? It's 3 to the I plus 1 minus 1 all over 3 minus 1, right? And sigma of 5 to the j would be 5 to the j plus 1 minus 1 all over 5 minus 1. Set that equal to 2 times 3 to the I times 5 to the j. Okay, you guys look at that while I erase for a minute. Okay, what do you think I might want to do next? We're looking for a contradiction. Yeah, Marissa?
Don't we know that the last line is an integer?
Yeah, this whole thing is an integer, this whole thing is an integer. This is number theory, right?
Yeah,
Well, number theory is the study of integers. Okay? So, what do you think? Fundamental theorem of arithmetic. I would love to do that. I think we're one step ahead of the game on doing the fundamental theorem of arithmetic, though. What would make this look nicer? Simplify it, right, by taking the denominators, right? I don't like those denominators there. It makes it look like fractions, right? We don't really want to have fractions here. Let's take, this denominator is just 2. This denominator is just 4, right? And then there's another 2 over here. So if I just take all those 2's and put them on the other side, I won't have any more fractions, right? So I'm just going to rearrange this expression. And it's going to look like 3 to the I plus 1 minus 1 times 5 to the j plus 1 minus 1 equals 16 times 3 to the I times 5 to the j. Okay, that's definitely a good idea. Let me just multiply out the left side. Just see what that gives me. So if I just multiply out the left side, I have 3 to the I plus 1 times 5 to the j plus 1. And then I have minus 3 to the I plus 1 minus 5 to the j plus 1 plus 1 equals 16 times 3 to the I times 5 to the j. Is there any way to put any of those terms together? It's a lot of a mess of an expression right now.
If you subtract 3 to the I plus 1, 5 to the j plus 1 from both sides, then you can pull up 3 to the I, 5 to the j on both terms.
Yeah, do you see, if you look here at the very first term, if you take one of those factors of 3 and one of those factors of 5 out, it'll leave you with I factors of 3 and j factors of 5, which will be then comparable with the 3 to the I, 5 to the j on the right side. That's really the trick here. That's basically what James is suggesting. Let me just rewrite this one more time. Okay, so we have a total of 15 factors of 3 to the I, 5 to the j on the left side, and we have 16 factors of the same thing on the right side. So if I just subtract them over, I'll be left with none of them on the left side anymore, so just the rest of the terms on the left, but I'll have one factor of the 3 to the I, 5 to the j on the right side of the equation. I'm hoping that this is starting to look a little more contradiction-like. Don't think too hard. What's wrong with this? What is wrong with this? You should be able to just look at it.
The left side's less than 0, the right side is not.
Yeah, look at the right side is positive for sure, but on the left side you've got a lot of negative stuff here, right? So adding 1 to that, it's still negative. So the left side, the left-hand side, I'll abbreviate LHS, is less than 0. The right-hand side is greater than 0, and that implies that we have a contradiction. We have a contradiction. Okay, so that's exactly how you want to do that. So just a little bit of practice, reminding you about the sigma. Okay, it's multiplicative, right? As long as the factors are relatively prime, you just split things into their prime factorization. You can use the multiplicative property, and then sigma of any power is just this formula right here. Okay, make sense? Everybody good with that? Okay, let me come back over here. Let's do another example. I'm jumping around. I'm doing problems from different parts of the semester in random order, partially because that may be on the exam. I don't know how I'm going to exactly structure it yet, but I may not put the problems in order of chronology of the material. So I want you to be able to handle things in any order. So let's do this one next. Let's compute the Legendre symbol of 182 relative to 421. Okay, these are, once you get the hang of these and the properties that you have, these kind of problems are fairly routine. What's on the bottom has to be a prime. Okay, so you know that 421 is a prime even if I don't tell you that it's a prime. You have to assume that that is a prime, and make sure that you never put something on the bottom of a Legendre symbol that's not a prime. Has to be prime, okay? So we have properties of this Legendre symbol. We can factor the numerator, okay? You cannot factor the bottom because the bottom is a prime, but you can factor the top. Any perfect squares that you run into on the top can be thrown away, right? They're going to be factored out of the whole expression. At the end of the throwing away the perfect squares, what you're going to have on top is going to just be single prime factors, right? Now we have a formula for the Legendre symbol of 2. If one of our prime factors on top is a 2, I just want to remind you guys, this is one of the theorems, right, that you guys are learning. This one is equal to 1 if, you remember? 1 or 7 modulo 8, exactly. And it's equal to negative 1 if 3 or 5 mod 8, exactly. So in the class, I proved the p congruent to 1 and 3 case, right? And then the other 2 cases are similar. So if you're working on this proof for the final, you just need to worry about the first 2 cases, and then the rest of it is just similar. But that's a useful thing. And then if you have any other odd prime, on the top of a Legendre symbol, what you can do is flip this thing upside down, right? You can flip this one over with a plus or a minus depending on the P and the Q, right? So it equals, let me just do 2 cases here. It's the exact same thing if P or Q is congruent to 1 mod 4, and it's the negative of that exact thing if both P and Q are congruent to 3 mod 4. Okay? The other really useful thing that you want to keep in mind is that if A and B are congruent to each other modulo P, then their Legendre symbols are the same, right? So, so it just goes this way. If A is congruent to B mod P, right? Then you can take whichever one is bigger, replace it with a smaller one. So in this way, you just basically want to keep reducing these numbers. Okay? So this is fairly recent. We just did this in April. So just kind of reviewing here. So based on all of that background, this is mainly what you would need. There is one other little fact. I'll just remind you of it here, that you can brute force this thing. The Legendre symbol of A with respect to P is congruent to A to the, remember what the power is? P minus 1 over 2 mod P, right? This is the Euler criterion. So that's kind of a nice one to remember, but you know, if your prime is really big, this is going to be a big power of A that you have to calculate. So that's a little more computationally intensive. Okay? I actually prefer to use the stuff over here and just keep reducing the numbers down. Okay, so I've given you guys a lot of while I've been doing the overview there, I've given you a lot of time to think about how you want to handle this one. Can somebody help me with this one? How does 182 factor?
2 times 91.
2 times 91. How does 91 factor? 7 and 13. You know, 91 is the smallest prime that, 91 is the smallest non-prime that most people think is prime. And people just don't notice that 91 actually does factor as 13 times 7. That would be the easiest RSA number to work with, right? P times Q of 91. Yeah, so anyway, that totally breaks down like that. Now in modulo, so the first thing I'm looking at here is the 2. What is 421 modulo 8? Because I want to use this top thing here. So if I take 421, you can use a calculator if you want, but if I divide it by 8,